Hello students, welcome to the class. So in the previous class, we have discussed what is equilibrium constant. Yes, and we know how to define equilibrium constant. Kc is equal to what? It is equal to the ratio of, okay, we'll take it here better. So here, equilibrium constant. Yes, equilibrium constant Kc is equal to what? It is equal to the ratio of, correct, product of molar concentrations of products raised to their coefficients, stoichiometric coefficients, to the product of molar concentrations of the reactants raised to their stoichiometric coefficients. This is Kc, right? So now, and we have also seen what is Kp, equilibrium constant when partial pressures are being considered. Yes, we define Kp when we consider partial pressures, we define Kp as how? We define it as partial pressures, product of partial pressures of the products divide to the partial pressures, product of partial pressures of the reactants to the reactants. Yes, and we have seen the relation between Kp and Kc also. So Kp is equal to what? It is equal to Kc into RT delta N, where delta N is total number of gaseous molecules, which is equal to number of gaseous molecules of product minus number of gaseous reactants. So this is what delta Mg stand for. Yes. So as a rule, the concentration of pure solids and pure liquids are not included when you are writing the equilibrium equation. Okay. Now moving to the next one, that is characteristics of this equation. So what are the characteristics? And we are going to discuss applications. Characteristics of equilibrium constant. So what all is required? See, when we speak about equilibrium constant. Okay. The first one is the value of equilibrium constant. It is independent of original concentration. Yes, the value of Kc, that is equilibrium constant, is independent. It is not a dependent on. It is independent on the initial concentration of reactants. So here, what does we mean by this? See, we cannot say that if we are taking more amount of reactants, then the value of Kc differs. If we are taking less amount of reactants, then the value of Kc will differ. No, it is independent of the initial concentration of the reactants. Second point is, the equilibrium constant has a definite value for every reaction at a particular temperature. So equilibrium constant differs for reactions. Equilibrium constant differs for different reactions and at different temperatures. Correct? Different temperatures. So when we are speaking about equilibrium constant, we consider a particular reaction at a particular temperature. Third one, for a reversible reaction. Okay, the equilibrium constant for forward reaction is inverse of the equilibrium constant for backward reaction. So the equilibrium constant for, it is Kc. The equilibrium constant for forward reaction is inverse of equilibrium constant Kc for backward reaction. Yes, backward reaction. So how do we represent it? Yes, I'll show you how do we represent it. So equilibrium constant for forward reaction. So if you are writing the equation, Kc is equal to C raised to C into D raised to D divided by A raised to A into B raised to B number of moles. Correct? So A and B are reactants, C and D are products. So this is for what? This is for forward reaction. Okay. Then what will be for backward reaction? For backward reaction, equilibrium constant will be inverse. Therefore, Kc inverse I will represent. It will be inverse. So 1 by Kc. Therefore, Kc inverse can be written as molar concentrations, product of molar concentrations of the reactants to the product of molar concentrations of the products. Yes, this is we write for backward reaction. So in general, the equilibrium constant, so I can write here equilibrium constant. Yes, we'll take a fresh page. Equilibrium constant Kc for forward reaction is inverse of equilibrium constant Kc for backward reaction. For backward reaction. Yes. Next point. The value of equilibrium constant tells the extent to which reaction proceeds in forward or backward reaction. So Kc tells us what? The extent in which the reaction proceeds in forward or backward reaction. Next point is equilibrium constant is independent of pressure of the catalyst. Presence of catalyst. So it is independent of presence of the catalyst. Does not depend upon the catalyst, because what work the catalyst does, we can discuss this once again. Yes, when we come to very important concept. Whenever a reaction is reversible, if you add a catalyst, what will happen? The reaction, with what speed the forward reaction is increasing, with the same speed the backward reaction also increase. So both the forward reaction rate and backward reaction rate are increased at the same rate by addition of what? By addition of catalyst. Therefore, Kc will not depend on the presence of the catalyst. Next, the value of equilibrium constant changes with, so it is dependent on temperature. Dependent on temperature. So thermodynamically, it can be shown that if suppose I say K1 and K2 are equilibrium constants of a reaction at absolute temperatures, say T1 and T2, then delta H, and if delta H is what? It is heat of the reaction at constant volume. Then I can write log of K2 minus log of K1 is equal to minus delta H divided by 2.303 R into 1 by T2 minus 1 by T1. Yes, this is called as Van 't Hoff's equation. What it is called as? Van 't Hoff's equation. It is called as Van 't Hoff's equation. So the effect of temperature with this equation, the effect of temperature, can be studied in three cases. Yes, which are the three cases? First one, when delta H is equal to 0. When delta H is equal to 0, what does this mean? It means neither heat is evolved nor heat is absorbed. Correct? Heat is absorbed. Yes or no? So neither there is absorption of heat nor there is evolution of heat. Yes, nor there is release of heat. Therefore, what happens to the equation? Log K2 minus log K1 is equal to, since delta H is 0, entire thing becomes 0. Yes, or I can write it as log K2 is equal to log K1. Log K1, yes or no? Or remove log K2 is equal to K1. Yes, so if delta H is 0, what will happen? K2 will be equal to K1. K2 will be equal to K1. Is that right? So K2 and K1 are what? They are equilibrium constants at two different temperatures, T2 and T1. Second one says that, thus here what I can say, equilibrium constant remains same at all temperatures. When delta H is 0, equilibrium constant remains same at all temperatures. Second one, if delta H is positive. If delta H is positive. Yes. What does that mean? It means heat is absorbed. Correct? Heat is absorbed. So when heat is absorbed, what type of reaction it is? The reaction is endothermic. Is that right? The reaction is endothermic. Thus, temperature, when heat is absorbed, if there are two temperatures, T1 and T2, which one will be higher when heat is absorbed? T2 will be greater than T1. T2 will be greater than T1. Therefore, what will happen to the equation? Log K2 minus log K1. We know that the equation is minus delta is 2.72, 1 by T2 minus 1 by T1. Yes, therefore, since T2 will be greater than T1, what I'll get? I'll get value positive. I'll get positive value. Or I can say, or log K2 is equal to positive value into this. Therefore, K2 will be more than log of K1. Or in general, I can write K2 is more than K1. Is that right? So this is possible when what? When temperature delta H is positive. What does that mean? It means heat is absorbed. For endothermic reactions, this is the case. So what we can say here, the value of equilibrium constant is higher at higher temperature. So in case of endothermic reactions, the value of equilibrium constant is higher at higher temperature, correct? High temperature. Yes or no? Please do remember these points because next concept very important that we come across all these things once again. Now third case is when delta H is equal to negative. What does that mean? Heat is released. Heat is released. So when heat is released, we call it the reaction is exothermic. So when the reaction is exothermic, naturally the temperature T1 is higher than T2. So T1 is higher than T2. Yes or no? Okay. Therefore, log of K2 minus log of K1 becomes what? It becomes negative. Or log of K2 will be less than log of K1. Yes, log of K2 will be less than log of K1. Or I can say K1 is more than K2 or K2 is less than K1. Yes or no? So K1 is more than K2. So I can say K1 is more than K2. Yes. So this is possible when delta H is negative. So when delta H is negative, this is the case followed. So what will happen? What does this mean? It means that the value of equilibrium constant is lower at high temperature. See here, we come across three conclusions from these three effects. The first conclusion is what? The first conclusion is the effect of temperature. What happens? Equilibrium constant remains same at all temperatures when delta H is 0. This is the first conclusion. Second one, for endothermic reactions, where delta H is what? Delta H is positive. What I can say? What we say? The equilibrium constant is higher at higher temperature. Correct? Higher at higher temperature. And third one, for exothermic reactions. For exothermic reactions, where delta H is what? It is negative. Yes, we say equilibrium constant is lower at higher temperatures. It is lower at higher temperatures, correct? And we come to these conclusions because in the first case we have seen, we'll take it like this. In the first case we have seen K2 is equal to K1 when delta H is 0. In the second case, so this is in the first case. In the second case, we have seen that K2 is greater than K1. Yes. And in the third case, we have seen K2 is less than K1. Is that right? So these are the three characteristics of equilibrium constant. Yes, these are the three characteristics. So very important characteristics. Apart from these simple characteristics, what we have discussed. These are all the characteristics what we have discussed, and dependent on temperature, we have these characteristics. Correct? Moving to the next point. The value of equilibrium constant depends on, yes, seventh point it is, value of Kc. Value of Kc, very important, depends on stoichiometric coefficients, or it depends on, you can say it depends on stoichiometry of reaction. Stoichiometry means what? How many moles, how many molecules are involved in the reaction. For example, let me say, so let me take an example. So let me say that SO3, gaseous SO3, it decomposes and the reaction is reversible. It gives me SO2 plus O2. and both are gaseous again. Okay, so both are gaseous. Yes, and I can write this reaction, same reaction as S. Okay, we'll balance it here. I'll write SO2, O2, 4 are there. So I will balance it by writing 2 and here 2. So 3 2s are 6, 2 2s are 4 plus 2 is 6. Yes, correct. Or I can write this reaction as SO3 gaseous. Yes, it decomposes, reversible reaction, SO3 plus O2. And here these are also gaseous, but here what I will do, balancing it like this, I will write half O2 here. So 3 plus 1, half O2. I'll represent it. Yes, this is SO2. Okay, it is SO2. I'll get SO2 sulfur dioxide plus O2. So here 3 oxygen atoms, here also 3 oxygen atoms come. So write equilibrium constant for this equation. Let me see. So when we write equilibrium constant for this equation, Kc is equal to products. So here concentration of SO2 raised to 2, concentration of O2 raised to 1 divided by concentration of SO3 raised to 2. Correct. Here you write equilibrium constant. It comes to Kc is equal to concentration of SO2 raised to 1, concentration of O2 raised to half divided by concentration of SO3 raised to 1. Yes, so both equilibrium constants are different. Therefore, I say value of Kc depends on what? It depends on the stoichiometric calculations. And we can say, so here this is K prime. So Kc prime is equal to what? It is root of K. Or I can write it is equal to K raised to 1 by 2. Okay. Similarly, at a particular equation, if a particular equation is multiplied by 2, yes, here from that we come to conclusions. If equation is multiplied by 2, okay, the equilibrium constant, the new, suppose there is a equilibrium constant, say, okay, say Kc. And if the equation you are multiply by 2, you will get new equilibrium constant Kc prime. That will be equal to square of the equilibrium constant. So it will be K square, Kc square. This is original one. When you multiply it by 2, the new equation will be Kc square. Second point, if the chemical equation for a reaction is written in 2 steps, say equilibrium constant for first step is K1, for second step is K2, then the equilibrium constants are related as K is equal to K1 into K2. K is equal to K1 into K2. So this is value of Kc depends on what? It depends on the stoichiometric calculations. So these are what? These are all the characteristics of equilibrium constant. So value of Kc, it is independent of the initial concentration of the reactants. Kc differs for different reactions and at different temperatures. For a reversible reaction, Kc for forward reaction is inverse of Kc for backward reaction. So if this is forward reaction, when you take backward reaction, it will be inverse. Yes. Next, Kc, so I'll represent it like this. Yes, or we can write it as Kc is equal to 1 by Kc. So this is for forward reaction, this is for backward reaction, and this is indicated as Kc prime. Fourth point is value of equilibrium constant tells the extent to which the reaction proceeds. So extent. Then it is independent of the presence of catalyst. It is dependent on the temperature, and we have this equation for temperature dependence. We have this equation for temperature dependence. Correct? This equation is for temperature dependence. So log of K2 minus K1 is equal to minus H upon 2.303 1 by T2 upon 1 by T1. And based on this, we can take effect of temperature. If delta H is 0, if delta H is positive, if delta H is negative. That is, neither heat is absorbed nor released, heat is absorbed and heat is released. That time what happens to the two equilibrium constants? So it remains constant at all temperatures when delta H is 0. Endothermic reactions, delta H positive, Kc is higher than at high temperatures. Exothermic, Kc is lower at high temperatures. Then value of Kc depends on the stoichiometry of the reaction. How many molecules are involved? Yes. Moving to the next one, that is applications of equilibrium constant, where all we can apply this in while carrying out chemical reactions, where we can apply and what all information we get from this equilibrium constant. So what are the applications of equilibrium constant? Okay, the first one, it is helpful in judging. It is helpful in judging the extent of reaction. Extent of reaction. It helps us to judge the extent of reaction. For example, yes, here we have points to remember. If I say, if Kc, that is equilibrium constant, is more than 10 raised to 3. It is more than 10 raised to 3. It means what? It means product predominates over reactant. Product predominates. Predominates over reactants. So product predominates means what? It means the reaction is proceeding towards product side. Understanding? So if I say this is my reaction, so this is reactant and reversible, and this is product. Correct. So now product predominates over reactant means product is more. That means reaction is proceeding in forward direction. Therefore, what can I say? So if Kc is very large, yes. So if Kc is very large, so if Kc is very large, that is Kc is more than 10 raised to 3, then I can say reaction proceeds in forward direction largely, forward direction largely, or you can say reaction proceeds almost to completion. Almost to completion. First point. Is that understood? So product predominates. If Kc is very large, product predominates. So it proceeds almost to completion. Second point. If Kc is less than 10 raised to minus 3. It is less than 10 raised to minus 3 means reactants predominate over products. So reactants predominate over products. So what does that mean? It means reactant is more means what? Backward reaction is more, or hardly the reaction has started. Can I say? Hardly reaction has started. Therefore, reactant concentration is more. Therefore, if Kc is very small, yes or no? See there, 10 raised to minus 3. If Kc is very small, what does that mean? The reaction hardly starts. Yes, the reaction hardly proceeds at all. Proceeds at all. Yes or no? Proceeds at all. Understanding? So this is the understanding. Third point, if Kc is in the range, yes, it is in the range of, say, 10 raised to minus 3 to 10 raised to plus 3. So this is first extreme, this is second extreme. If it is in between range means what? Appreciable concentrations. Appreciable concentrations of both reactants and products are present. Yes or no? Are present. So I cannot say reactant predominates, nor I can say product predominates if it is in this range. Yes. So if Kc is very large means what? Kc is more than 10 raised to 3. Reaction proceeds in forward direction. Product predominates. So if Kc is very large, what does that mean? It means product predominates. So product predominates. Correct? So product predominates if Kc is very large. Okay. And if Kc is very small, then what? Reactant predominates. Reactant predominates. If Kc is very small, reactant predominates. Yes. And if Kc is in the range of this and this, appreciable concentration of both reactants and products are present. Appreciable concentration of both reactants and products are present. So this is the first application. That is, it helps in judging the extent of reaction. I can show you like this also. We can discuss it like this. Yes. So let me say I have the reactant Let us consider it like this. So let us say that this is progress of the reaction. Here I have reactants. And here I have products. Okay, so here how I can show is, and this is this is progress of the reaction. This is progress of the reaction. Okay, here, so if I mention in between Kc, if I mention here Kc, okay, then here I will say it is here. You have to answer me. How is Kc here and how is Kc? Okay, you have to tell me how is Kc here and how is Kc here. So you can see the position of Kc. This is from reactants to products. Okay. So here how is Kc? Kc is very less. So can I say Kc is less than 10 raised to minus 3. So Kc is very small here and here Kc is very large. Almost at the end, right? More than 10 raised to 3. So Kc is very large. And this is the range. This is the range between so and so. So at this case, what I can say? I can say that here reaction proceeds hardly. Proceeds hardly at all. Hardly at all. At all. So when Kc is very less, reactant concentration predominates. Yes. When Kc is very small, very large, reaction proceeds for completion. Yes, proceeds for completion. Yes or no? Can you see this? It proceeds for completion. So that time, which concentration predominates? Product concentration predominates. But when it is in this range, when it is in this range, what I can say? When it is in this range, between 10 raised to minus 3 to 10 raised to plus 3, what we can say here? We can say that both reactants and products, I am not saying they are present half. Yes, they are present in appreciable amounts. Are present in appreciable amounts, or you can say they are present at equilibrium. Correct? They are present at equilibrium. So this is the first application for judging what? For judging the extent of the reaction. For judging the extent of the reaction. Second application is, it is predicting the direction of reaction. Predicting the direction of reaction. Okay, now how can we predict the direction of the reaction? Now see, concentration ratio is what? Ratio of product concentrations of the products to that of reactants is also known as concentration quotient. Now see, when we speak about equilibrium constant, we say Kc is equal to product concentration of concentration of the products raised to C and D to product of concentrations, molar concentrations of the reactants raised to their stoichiometric coefficients. Correct? This is at equilibrium. Yes, when the reaction has attained equilibrium. But what if it is somewhere at certain point before or after equilibrium? So here it is somewhere. So this is at equilibrium, right? So Kc product that require reaction. So if the reaction is here, 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 it will still have some quotient. It will still have some constant, and that is called what? That is called Qc. It is called what? Qc. Therefore, I can write Qc as same concentration of C into concentration of D upon concentration of A into concentration of B at any instant of time. At any instant of time other than equilibrium. At equilibrium, this is followed. Then what is Qc? Qc is called concentration quotient. It is called what? Concentration quotient. So Qc is what? It is the ratio of product of molar concentration of the products raised to their stoichiometric coefficients to the product of molar concentrations of the reactants raised to their stoichiometric coefficients at any instant of time, other than equilibrium. Because at equilibrium, we know this is followed. Yes. Therefore, can I say at equilibrium, QC is nothing but what? QC is nothing but Kc. Understood? I'll give you a simple example. Let me say I have a reaction A plus B gives reversible reaction X plus Y. So how do you write concentration quotient? I will write concentration quotient QC is equal to product of concentrations of the products to product of concentration of the reactants at any instant of time. Other than equilibrium. And how do you write equilibrium constant? Kc is equal to product of concentration of the products to the product of concentration of the reactants at equilibrium. Yes or no? At equilibrium. This is at any instant of time. So why it is required? So it may be noted that QC becomes equal to Kc at equilibrium state. Yes, when reaction has reached the equilibrium. Therefore, from this, what all information I can state? QC becomes equal to Kc when a reaction is at equilibrium state. Correct? Therefore, at equilibrium, I can say QC is equal to Kc, or it is equal to Kp, or it is equal to Kx. Yes, or it is equal to Kx. This is first point. Second point, if I say QC is less than Kc, what does that mean? It means the reaction will proceed in direction of what? Direction of reactants. Because QC is less than Kc. So reaction, if it is like this, Kc is here, let me say, QC is less, so it is less. So it will proceed in the direction of the reactants. Okay. Third point, if QC is if it is less than Kc, then reaction will proceed in the direction of products. Correct? Less than Kc. Or you can say it will proceed in forward direction. Correct? It will proceed in forward direction because see, Kc is here. Let me say for this reactant. Okay, we will take it like this. Standardly, we will write the reaction. Then it will make us understand. Okay, we'll take here. So if the reaction is like this, okay, so let me say this is reactant and this is product. And let us say that this is our somewhere at this point, Kc is there. Now rest other than this point, all the other points become what? Qc. Yes, quotient, concentration quotient. So if Qc is less than Kc means what? Qc is somewhere here. So if Qc is less than Kc, then to attain equilibrium, reaction will proceed how? It will proceed like this. So which is that reaction? It will proceed in forward direction. That is, it will proceed in the direction of products. Now, if Qc is more than Kc, then what will happen? Reaction will proceed in direction of what? It will proceed in direction of reactants. Yes, it will proceed in the direction of reactants. So we can show here. So if the reaction is here. Correct? Now this is reactant and this is product. Okay. This is my product. Now here, where is my Kc? Say somewhere here is my Kc. Other than this, all become what? Qc. Now here what they have said, Qc is more than Kc. So Qc is somewhere here. So reaction has to proceed. It should proceed how to reach Kc? To attain equilibrium, it should proceed in this direction. And what is this direction? This is nothing but backward direction. It is backward direction. Yes, that means reaction is proceeding towards what? Towards reactants. Towards reactants. And fourth point is same point as first. If Qc is equal to Kc, what does that mean? Again, take this. Reactant you have, and here you have product. Yes, Qc is equal to Kc means what? Yes, this is there. And then I will indicate. So if Kc is here, then Qc is equal to Kc means what? Qc is also here only. What does that mean? Will the reaction proceed anywhere? No, because Qc is equal to Kc means what? It means the reaction is at equilibrium. Is at equilibrium. And we have appreciable amounts of both reactants and products. Appreciable amounts of both reactants and products. And this I have indicated here with the pictorial representation. You can see. Okay. So here you can observe. Qc is equal to Kc. So Qc is equal to Kc, equilibrium. So Qc is equal to Kc at equilibrium. If Qc is less, can you see this is less than Kc? So if Qc is less than Kc, reaction will proceed in forward direction. So product is predominating. Product is predominating. If Qc is more than Kc, can you see it? Qc is more than Kc, reaction will proceed. So this is equilibrium. So let us say here like this. So this is the progress of the reaction, let me say. This is the progress of the reaction. Then I will indicate it like this. So if Qc is less than Kc, so Qc is somewhere here. It is less than Kc. Therefore, what will happen? Reaction will proceed in forward direction. It will proceed in forward direction so that equilibrium is attained. Yes, equilibrium is attained. If Qc is more than Kc, so it is more, it is somewhere here. Then reaction will proceed how? It will proceed in backward direction to attain the equilibrium. It will proceed in backward direction to attain the equilibrium. So if Qc is less than Kc, then product, it will proceed in the direction of products. If Qc is more than Kc, it will proceed in the direction of the reactants. Yes. So this is the applications of equilibrium constant. It is the applications of what? Equilibrium constant. Yes. So I hope the characteristics of equilibrium constant and the applications of equilibrium constant are quite clear. So equilibrium constants representation, Kc, concentration of reactants and products. So we represent it like this. Then Kp, partial pressures of reactants and products only for the substance which are in gaseous state. Okay. So we represent it like this. Kx, mole fraction of reactants and products. We represent it like this. Okay. Relationship between Kc, Kp and Kx. So Kp is equal to what? Kc RT delta Ng. And Kp is equal to what? Kx partial pressure delta Ng, where delta Ng is what? Number of moles of gaseous product minus number of moles of gaseous reactants. Kc is the equilibrium constant expressed in terms of concentration of the reactants to products. Similarly, Kp is the constant in terms of partial pressures of the substance, and Kx is expressed in terms of mole fractions. So with all this explanation, what is the applications of law of mass action? This law is also applicable to semiconductors, like how we discussed about equilibrium constant. That is one application of law of mass action. It is also applicable to semiconductors. Therefore, has several important implications in the field of electronics and semiconductor physics. Here, the law of mass action provides a relationship between concentration of electron holes and free electrons. So in semiconductors, we have something called electron holes and free electrons, which act as current carriers. So when the semiconductor system is in the state of thermal equilibrium. Moving to the next one, types of chemical equilibria. The equilibrium between different chemical species present in the same or different phases is called chemical equilibrium. There are two types of chemical equilibrium. One is homogeneous chemical equilibrium and another one is heterogeneous chemical equilibrium. Yes, as the term suggests. So first one, homogeneous chemical equilibrium. So homogeneous chemical equilibrium means what? And then we will see what is heterogeneous chemical equilibrium. The equilibrium reaction in which all the reactants and products are in the same phase, They are in the same phase. So when all the reactants and products are in the same phase, gaseous phase, all are in gaseous phase. Liquid phase, all reactants and all products are in liquid phase. Solid phase, all reactants and all products are in solid phase. Then we call it as homogeneous chemical equilibrium. So let me take an example like esterification reaction. See, in esterification, we take an acid, acetic acid, CH3COOH, treat it with an alcohol, C2H5OH, yes, which is at equilibrium. We get CH3COOC2H5 plus H2O. Now, if you look at this reaction, this is esterification reaction where all the reactants, they are taken in liquid phase. Acetic acid, this is ethanol. The product what we obtain, both the products are also in liquid phase. So here, all reactants and all products are in the same phase. Therefore, this is an example for what? It is an example for homogeneous chemical equilibrium. Take another example, that is manufacture of ammonia by Haber's process. N2 gas, when it reacts with H2 gas, yes, a reversible reaction occurs at high temperature and pressure. We get ammonia in the form of gaseous state. Yes, balance this reaction. I will write here 2, here I will mention 3. So if you look at this reaction, the reactants, both the reactants and the product form, all are in what? All are in gaseous state. One more example, for during manufacture of sulfuric acid, this is the key step. During manufacture of sulfuric acid, this is the key step. It conversion of or oxidation of sulfur dioxide to sulfur trioxide. If you look here, sulfur dioxide and sulfur trioxide all are in gaseous state. Oxygen, sulfur dioxide, sulfur trioxide, all are in gaseous state. Understand? So the reaction in which, the equilibrium reaction in which all the reactants and all the products are in the same phase, we call it as homogeneous chemical equilibrium. Then what is heterogeneous chemical equilibrium? Heterogeneous chemical equilibrium. Yes. So heterogeneous chemical equilibrium means what? Fine. So heterogeneous chemical equilibrium means in which the reactants and products are present in different phases. They are present in different phases. We call it as heterogeneous chemical equilibrium. It is called as heterogeneous chemical equilibrium. Let us take an example to understand. Decomposition of a bicarbonate, say sodium bicarbonate, NaHCO3. I will take it as a solid. Sodium bicarbonate is solid. Equilibrium, reversible reaction. It gives me Na2CO3, which is solid. Plus there is evolution of carbon dioxide gas, plus there is evolution of vapors, water vapors. So you can see here the reactant is in solid, one of the product is solid, and some products are in gaseous phase. So this is called what? This is heterogeneous chemical equilibrium. Or you take lime water, calcium hydroxide plus H2O. So lime water, this is called lime water. Reversible reaction, it forms Ca plus 2 ions plus OH minus ions. Yes. So here if I want to represent the reaction, this is solid, water I have taken liquid. This is formed in ions, aqueous. This is also in water. Therefore, I will mention it as aqueous. So solid, liquid, and these are in aqueous state. So they are present in what? In different phases. Even decomposition of calcium carbonate. We know that calcium carbonate, limestone, it is solid. It will decompose to give calcium oxide which is solid, plus carbon dioxide gas, which is gaseous in nature. So solid, solid and gas. So they are present in different phases. That's one more example you can take. Liquid water, that is our water, forming H2O gas. This is physical equilibrium. So here you can see it is different phases. We call it as heterogeneous chemical equilibrium. So what do we mean by homogeneous chemical equilibrium? Where reactants and products, all the reactants and all the products are in same phase. Heterogeneous chemical equilibrium, where the reactants and products are in different phase. So homogeneous chemical equilibrium, here different examples are taken. In this type, the reactants and the products of chemical equilibrium are all in the same phase. Homogeneous equilibrium can be further divided into two types. Reaction in which number of molecules of the products is equal to the number of molecules of the reactants. Correct? For example, you can see here H2 plus I2, two reactants, I'm getting 2 molecules of products. So number of molecules of products is equal to the number of molecules of reactants and all are in same phase. N2 plus O2 gives NO. All are in same phase, gaseous phase. 2 molecules of reactants, 2 molecules of product. And one more is reaction in which number of molecules of products is not equal to total number of reactant molecules. Here all are in gaseous phase. See, it is homogeneous. Here there are 3 reactant molecules total and here there are only 2. Here there is 1 reactant molecule and here we have got 2. Yes. So homogeneous chemical equilibrium means the number of all the reactants and all the products are in same phase. Further, it is divided into two types, where the total number of reactant molecules is equal to the total number of product molecules, as in this case, examples. Or the reactant molecules is not equal to the product molecules. It may be more or it may be less. So you can see here, this is a table to indicate homogeneous equilibria and equilibrium constants. Yes. So delta N is equal to 0, Kp is equal to Kc. Delta N is less than 0, Kp is less than Kc. If delta N is more than 0, Kp is more than Kc. So examples for homogeneous. H2 plus I2 gives 2Hi. All are in gaseous phase. Here delta N is equal to 0. Why delta N is equal to 0? Tell me. Because here there are 2 reactant molecules and 2 product molecules. So it is equal to 0. Less than 0. Why? When delta N will be less than 0, when number of product molecules, okay, we'll take different color. When number of product molecules is less than number of reactant molecules. So there are 4. So here 2 minus 4 is minus 2. So delta N is less than 0. More than 0, number of product molecules is more than number of reactant molecules. So 2 minus 1 is equal to 1. So it is positive, greater than 0. So these are the examples. All are homogeneous. So initial moles 1 and 1. Final is 0. Initially I have written. Yes. So 1, 1. Initially it is 0. Product is initially 0. Correct? Moles at equilibrium. So 1 minus x, 1 minus x. This is if I take it as x. So 1 minus x, 1 minus x. This will be 2x. 2 is the coefficient. Similarly here. Total moles at equilibrium. This we get. Then these are calculations. Active masses, mole fraction, partial pressures, Kc, Kp. These are the equations. Yes. So remember only this term. These as examples. Delta N is equal to 0. Kp will be equal to Kc. And please remember equation for Kp and equation for Kc. Similarly here. These two with examples Kc and Kp. Kc and Kp and Kc and Kp. Please do remember these itself. That's it. Yes. These solutions are not there for you. So, heterogeneous chemical equilibrium. Reactants and products of the chemical equilibrium are present in what? They are present in different phases. When they are present in different phases, we call it as chemical equilibrium. It is called as chemical equilibrium. Okay. So, see examples. CO2 plus C gives 2CO. Gas, solid, and carbon monoxide gas. Calcium carbonate decomposition, solid, gas. So they are in different phase. Thus, different types of chemical equilibrium are based on phase of the reactants and products. You can see this is for heterogeneous chemical equilibrium. All are the examples for it. And please remember only Kp equations. So Kp for such equation, it is P square by 4. Here it is, we do not calculate delta N here because it is only for gaseous, right? Here it is 4 into P x square by 1 minus x square, 4p cube by 27. Next concept, relation between equilibrium constant and, so let us see here, relation between equilibrium constant that is Kc and Gibbs free energy, that is, or you can say, I'll take it rather than saying Gibbs free energy, let us say standard Gibbs free energy, that is what, delta G naught, correct? Okay, now see, when we talk about equilibrium constant, yes, it is what, let us consider a reaction. Let me say that we have reaction A moles of A plus B moles of B, okay, gives, this is at equilibrium, reversible reaction, C moles of C plus D moles of D. Okay, now see, for the such reaction, how do you write equilibrium constant? Equilibrium constant, Kc is equal to what? It is equal to, okay, product of molar concentrations of the products raised to stoichiometric coefficients to the product of molar concentrations of the reactants raised to stoichiometric coefficients. Yes. So this is equilibrium constant, where see this represents concentrations. Okay. So according to this particular expression, it is equilibrium constant. What is Gibbs free energy? See, we have studied Gibbs Helmholtz equation, right? So according to Gibbs Helmholtz equation, standard Gibbs free energy. So Gibbs free energy for a reaction under any condition, it is related as delta G is equal to delta G naught plus 2.303 RT log K. Log K. Or here, first I'll say log K only. Yes, let me not write it as log Kc. Yes, log K. Okay, so standard free energy change of the reaction and its equilibrium constant are related to each other at a temperature T. This is at any temperature. So at a particular temperature T, I can write this equation like this. Excuse me. Delta G is equal to delta G naught plus 2.303 RT log, instead of K, I will write Kc, where Kc is what? Kc is equilibrium constant. Yes, yes, or this Kc expression can also be written as Kc is equal to A C raised to C into A D raised to D upon A capital A raised to A capital B raised to B. So what does A represent? It represents the activity of the reactants and products. And when we speak about activity, it is unitless quantity. It is unitless quantity. So for that, if for pure solids and liquids, if you have pure solids and liquids, A will be 1. A represents what? Activity. For gases, A is what? It is pressure of gas in atmosphere. And for components in solution, A is what? A is nothing but molar concentration. Correct? So when we have solids, we represent A as 1. We do not take it into consideration. For gases, it becomes A becomes P, pressure. And for components in solution, A becomes C, concentration. It becomes molar concentration. Yes, so this is the relation between equilibrium constant, Kc, and Gibbs free energy. Is that right? Yes, so delta G for the reaction under any condition is related with delta G naught. So delta G is equal to delta G naught plus 2.3 RT log K. Standard free energy change of the reaction and its equilibrium constant are related to each other by at certain temperature. So here we write Kc. For a general reaction, Kc is equal to, this is written where A represents what? It represents activity of the reactants and products, and it is unitless. For pure solids and liquids, A is equal to 1. For gases, A is equal to pressure of the gas in at atmospheric pressure in atmosphere. And for components in solution, A is what? It is molar concentrations. Molar concentrations. Yes. So this is the relationship between Kp and Kc. So in this class, what all we have discussed, very important concepts we have discussed, please try to understand them, because only if we understand them, we can explain any of the examples. Yes, so these are the characteristics what we have seen. Yes, and very important, this equation what we have seen, K2 minus K1. From this equation we get to know that it is dependent on the temperature. So here dependency of the temperature is given. Delta H is equal to 0. Neither heat is absorbed nor heat is evolved. So that time log K2 minus K1 becomes 0. What does that mean? K2 is equal to K1. Yes, we'll see. Next slide, we will see the conclusions. Delta H is positive means what? Heat is absorbed. That means we are talking about endothermic reactions. So T2 is greater than T1. So the value of Kc is higher at high temperatures for endothermic reactions. If delta H is negative, heat is released. T2 is more than T1. So K2 is less than K1. That means for exothermic reactions, value of Kc is lower at high temperatures. So we come to these three conclusions. Kc constant, equilibrium constant, remains same at all temperatures when delta H is equal to 0. For endothermic reactions, that is H is positive, Kc is higher at higher temperatures. For exothermic reactions, delta H is negative, Kc is lower at higher temperatures. And these are the three expressions for it. Next, we have seen value of Kc depends upon the stoichiometry of the reactions. Yes, and that also is given. If the reaction is multiplied by 2, Kc will be square. We have different. When we take examples on it, you'll get to know. Yes. So if you have different steps, Kc will be product of the equilibrium constants of each step of the reactions. Then we have seen applications of Kc, judging the extent of the reaction. Kc is very large, means what? 10 raised to 3, product predominates. Reaction proceeds in forward direction. Kc is very small, less than 10 raised to minus 3, reactants predominate over products. That means the reaction hardly proceeds at all. Kc in the range of 10 raised to minus 3 to 10 raised to 3, appreciable concentrations of both reactants and products will be present. And this is how we indicate. We indicate the reaction. So here if you see if this is the product proceeding of the reaction, if reaction is proceeding in this direction, so what does that mean? It means that here somewhere Kc is attained, let us say, then Kc is very small, 10 raised to minus 3, reaction hardly proceeds. Concentration of the reactant will be more. And if Kc is very large, reaction proceeds for completion. Product concentration will be more. If Kc is here, it means reactant and products are in equilibrium. Second is predicting the direction of the reaction. We have something called concentration quotient here. So at any instant of time other than equilibrium constant, we have Qc. So Kc, we know this. Qc is what? Ratio of product of concentration of the products raised to stoichiometric coefficients to the product of concentration of the reactants raised to stoichiometric coefficients at any instant of time. And at equilibrium, what happens? Qc will be equal to what? Qc will be equal to Kc. It will be equal to Kc. So I can write Qc like this and Kc like this. I represents what? At any instant of time. Yes. And with this, what information we get? If Qc is equal to Kc means what? Reaction is at equilibrium. If Qc is less than Kc, then to attain equilibrium, reaction will proceed in forward direction. You can see this graphical. That means it will proceed in the direction of products. If Qc is more than Kc, then reaction will proceed to attain equilibrium. Reaction will proceed in backward direction. That is, it will proceed in the direction of reactants. And if it is equal to Kc means what? It is at equilibrium. Then types of chemical equilibria, there are two types of chemical equilibrium. One is homogeneous chemical equilibrium and another one is heterogeneous chemical equilibrium. All reactants and products are in same phase. It is homogeneous chemical equilibrium. And in that also we have two types. If the total number of reactant molecules are equal to total number of product molecules, and we have one more type wherein the number of reactant molecules is not equal to number of product molecules. And these examples, what you are seeing here, these are examples for these two are examples for second type. This is example for first type, correct? This is example for first type where number of reactant molecules is equal to number of product molecules. And here number of reactant molecules is not equal to number of product molecules. So it is 2 and here it is 4. Yes, so this is homogeneous chemical equilibrium. And here we have heterogeneous chemical equilibrium where reactants and products are present in different phases. Yes, and then lastly, we have seen the relationship between equilibrium constant Kc and standard Gibbs free energy. So equation is taken like this. For equilibrium constant involved, we write delta G is equal to delta G naught plus 2.303 RT log Kc, where Kc is what? Equilibrium constant. Kc is equilibrium constant. Is that right? So here Kc is written in this format. We have come across another form where A represents what? A is nothing but activity of reactants and products. So for solids and liquids, A is 1. For gases, we take partial pressure. For components in solution, we take molar concentrations. Yes, so this is all about chemical equilibrium. Now we have something which affects the chemical equilibrium and equilibrium constant. That is nothing but Le-Chatelier's principle. So we have Le-Chatelier's principle and the applications of Le-Chatelier's principle. Very important concept. So this we will be taking up in the next class. We'll be discussing Le-Chatelier's principle and what are the significances of Le-Chatelier's principle and what are the applications of Le-Chatelier's principle that we will be discussing in the next class. I hope whatever I have explained so far regarding applications of law of mass action or regarding this characteristics of equilibrium constant and applications of equilibrium constant, relationship between Kc, Kp, Kx, all these things are being followed. Yes, so in the next, please practice all the concepts very properly so that when we are tickling the questions, yes, it becomes easy. If you know those things, we can easily predict what is equilibrium constant in our multiple choice questions. Yes, in the next class, I'll move to the next concepts of the topic. For now, thank you.